Alright, hey everybody. So, today we're going to be talking about stacks, queues, and decks. This is going to be a theory video, as we do usually. So I'm going to go through, talk about them, and then we'll have a separate video where I go through and actually implement these things in Rust. Now, these are very fundamental data structures. They really run most of the world, man. They're very simple, and what they do is they kind of encode different rules about how things flow through a system. And I kind of talk about this later in the lesson, but oftentimes students are like, well, why don't I just use a deck everywhere? On top of that, why don't I just use a ring buffer everywhere? And so knowing the differences between stacks, queues, and decks, and knowing when to use them is very important, and it makes your code a lot easier to reason about when you use the appropriate data structure for the problem. Okay, so let's get started. All right, so let's talk about stacks. Right, so last in, first out stuff. Right, so you'll often hear this data structure referred to as like a stack of plates. Right, you push your plate on the top, take a plate off the top. Right, like in a country ass buffet, they got the things stacked up and you take the plates off the top. That's how a stack works. And so you'll see that each one of these has rules, right? So a stack has a rule, a queue has a rule, a deck has a rule. Okay, so stack rules, you can only insert or remove at the one end, the top, right? So what problems do this solve? Pretty simple, right? Take on the top, remove on the top. So what do you solve with that? Well, obviously, undo, redo in an editor. Pretty obvious there. Browser history. Depth first search. I actually have a video on depth first search, so go watch that if you're interested in that. And managing function calls on the call stack, right? Literally the entire stack of a running program, it's a stack, right? So a little example other than the plates example, right? So imagine you're climbing a tower of crates in a warehouse and you can only place new crates on the top. When you remove one, it's always the crate you last touched. Remember, stacks are last in, first out, right? So the last thing you put in is the first thing you're going to take out, okay? Now, so you'll see across the board these things are pretty much constant time. Now, searching inside, I added this because students have asked about this. It's linear, but this is something that you do not do in a stack, okay? A stack is built around the rule that you only ever interact with the top, okay? Push goes to the top, pop removes from the top, peek looks at the top, right? Everything about a stack assumes you are treating the data structure like a stack of plates, or you're only touching the top one, okay? If you try to search for something inside, you're breaking the entire idea, right? I mean, the idea of a stack is this: putting it on, taking it off, right? And it would also require a full linear scan, right? So you'd have to start from the top, look at the next item, next item, next item, next item, until you maybe find it. And if you have a lot of items and you never find it, that's a big wasted operation, okay? And so searching violates the entire idea behind a stack, okay? And so here's the Rust shape. You'll see that we're going to be implementing it as a vector, right? Now, queues. First in, first out. So for queues, you insert the back and you remove from the front. Okay, so that's the rule for queues. That's what you use them for, right? And so with queues, it's really about anything about fairness or ordering. Okay, so print jobs, task waiting for processing, breadth first search, which I'm doing a video on. It may be up. You can go check it out. Network packets waiting to be handled, and message queues, Rabbit, Kafka, Redis list, things like that. The network packet bit, that's typically a ring buffer, but that's besides the point. It's kind of waiting to be processed. Okay. If the system needs to process items exactly in the order they arrived, a queue's the way to go, right? And so, it's like being in a cafe, right? People walk up and new people join the back and the person at the front is served next, right? So you are processing items in the order they arrive. Okay, first come, first serve. So remember, queues first in, first out, across the board. So you'll see these terms. So these are just terms for pushing, popping, and looking at the primary element, which in a queue is the front element, right? Now these are implemented with Deques, which we'll talk about. I'm actually thinking about maybe doing a video just on the Deques type in Rust. So now let's talk about Deques, right? So these are two-ended queues, right? So a deck it's like a wild card, right? It behaves like a stack and a queue. You can push and pop from both ends of it. So the deck rule, right? So two ends, both usable for insertion and removal, right? The front and back are symmetrical, right? This just means that the front and the back behave the same way, right? So a stack has one operational side, the top, and then a queue has one entrance, the back, and an exit, the front, right? They're not interchangeable. A deck does not tell you which end, front or back. You decide on that, right? And the symmetry of the ends is really where all the flexibility comes into play, right? So what problems do they solve? Anywhere where you need flexibility at both ends, okay? So sliding window algorithms, palindrome checking, BFS variants that reinsert nodes at different positions, job schedulers allowing priority, and then undo and redo behavior. Now I want to talk about this one, right? Because queues are used in priority-based systems, but they don't, there's no like priority queue, right? So like I mentioned priority and job schedulers, right? There is no priority queue behavior. Since a deck lets you insert on either end, you basically simulate these levels of priority. So, you know, task push to the back are considered normal priority, and task push to the front are urgent, right? So this is a natural pattern in schedulers, BFS variants, and you know some OS processes, right? It is not like priority like a binary heap, right? It's like a skip the line priority. So right, imagine like a call center, right? So regular callers join the queue at the back, and then emergency calls get inserted at the front, right? And so here you've created a normal queue plus a simple jump the line rule, right? No extra data structures or anything is needed, right? This is why Deques get used in algorithms like the following, right? So 0, 1 BFS, right? So this is a graph algorithm where edges cost 0 or 1, and you want the shortest path. You can actually do this faster with a deck than Dijkstra, right? Which is a common algorithm to do that. If you take a 0 cost edge, you push the next node to the front of the deck, right? High priority. If you take a 1 cost edge, you push the node to the back, normal priority, right? It becomes a 2-level priority system, letting you process cheap edges sooner, okay? So this turns a potentially expensive shortest path problem into an OV plus E algorithm, right? Through the jump in line behavior. Now, I'll kind of talk a little bit about what that is here. Now, sliding window problems, right? So when you scan through an array with a window of fixed size, like max value in every window of width 3, right? You need to update the window as it moves, right? So a deck helps maintain just the bits you need, right? So new elements go in the back, old elements are dropping out of the window when they get removed from the front, and any element smaller than the new one gets popped immediately, okay? So sliding window max goes from linear time based on windows to just linear time because each element enters and leaves the deck at exactly one time, okay? Now, monotonic queue optimization. Okay, so this is a queue that keeps its elements in sorted order, typically decreasing. It maintains that item can only be removed from the ends and remove anything that breaks the ordering, right? So when you add a new value to a monotonic queue, you remove items from the back if they're smaller. because once a bigger value arrives, smaller ones can never become the max again, right? So that keeps the queue in that decreasing order. It's important in monotonic queue. That ordering is very important, okay? And then when you remove values from the structure layer, you only pop from the front, right? If the value at the front is the one being removed. The front always holds the current maximum, okay? And so this structure always keeps the best candidate at the front. So in the end, Deques provides structural flexibility without having to implement more complex data structures or fancy algorithms or stuff like that. Okay, so yeah, example, train track with stations at both ends. You can load passengers from either side, and you can unload passengers from either side, right? They're symmetric, flexible, and efficient. Now, as we'll see here, constant time across the board. Indexing. It's weird, okay? Once again, this is all about the rule, okay? So remember, a vec it's very simple, right? It's a simple contiguous block of memory, and indexing is trivial, right? When you're just dealing with a plain old vector, okay? Now, a vec-deque under the hood is a ring buffer, right? It has a tail and a head. And the logical sequence of elements may wrap around the end of the internal buffer. And physically, the elements are split into two segments, right? So like this. They're not contiguous, okay? And then you can compute the real memory index. Well, you can watch our ring buffer video, right? I did an implementation of a ring buffer. You can watch that, and we actually talk about, calculating the memory indexes to move the indexes forward or backwards, all right? The access time is still constant. Now, why is it awkward? Okay, because the data is not actually stored in a clean linear sequence if you had like a vector, right? So if you did this works, but it's misleading, right? Because you're not indexing into one clean memory block, you're indexing through a circular structure, right? That index could change, right? If it may not be there the next time, something may have taken its place, right? It's not meant as this consistent storage unit, this consistent type of storage, okay? So here you go, right? Indexing, it's not a common use case for Deques. Using both ends as the intended pattern. And like with the other ones, right? Like with searching in a stack, it defeats the purpose, right? It's not the intended pattern for this data structure, okay? It feels like you're breaking the abstraction. And so Deque indexing is constant because we can compute the real position. But it's awkward because the data is physically wrapped around like a loop and not laid out in order like a vector, right? So so this is kind of the behavioral summary of the three. So with the stack, we're inserting at the top, removing at the top, and it's a last in, first out. With queues, we're inserting at the back, removing from the front, and it's a first in, first out. With a deque, we can insert at either end, we can remove at either end, and it's either one we want, okay? So, stack is a pile of books. You can push and pop on the same end. Queue is a line of customers. You can push back, pop front. Double is a double-ended subway car, right? Push and pop at both ends. Now, here are some questions that have come up in classroom settings with me about this, okay? So, why not just use a deque for everything, okay? So, when you're writing code or architecting, whatever you're doing, right, you always want to go with the simplest solution. And in this case, you want to always go with the simplest data structure that matches your problem. Okay, well, why? Okay, well, correctness. Okay, so stacking queue rules encode intent. If you use a deque everywhere, you lose that safety guardrail, right? Because if your problem only needs things to be pushed and removed from the top, well, you want to implement a data structure that only allows that, or at least that when the maintainer comes and someone down the road picks up your code, they're like, oh, okay, well, this is a stack. I know how this works. But if you're using a deque like a stack or A queue, it's very confusing. It's like, well, why are you using a deck here, right? And that's where I go into communication, right? So a stack tells a future maintainer this code works in a last in, first out order. Don't change the order. A queue says this process must preserve arrival order, and then a deck says ordering rules are more flexible in this situation, right? If you use a deck for everything, this kind of muddies the self-documentation, right? A deck is a generalization, useful when you need it, noisy when you don't, okay? Now, why not just use a ring buffer instead of a deck? I've been asked that too. Well, so there are conceptual differences between a ring buffer and a deck, even though in Rust, a VEC deck is a ring buffer under the hood, okay? Ring buffers are great for overriding old data, if you want to. In the ring buffer video that we did, we don't overwrite data, okay? Streaming data, bounded queues, everything that we talked about, right? And they provide a consistent memory footprint. They don't dynamically shrink or grow. A deck is growable, shrinkable, double-ended. Okay, it expands when needed, contracts when needed, and it supports two ends, but it never overwrites existing data, right? That maximum value is popped off the top, and you're never going to see it again, okay? Now also the internal mechanics, right? So inside Rust, VecDeck is a ring buffer underneath, but it's a managed one, right? That grows when it gets full, okay? So with a ring buffer, you have a head index, tail index, wraparound logic, and manual capacity management. You'll see all that in the video if you watch it, okay? Now, and VecDeck, it just hides all that complexity and adds dynamic growth, two-direction operations, and there's no requirement for overriding semantics, okay? So here's where I kind of go into the differences between the ring buffer and the deck. All right, guys, so that's it. I'm going to post the link to this in the description, and then we'll get to the implementation. We're definitely going to do that this week. Like I said, I wanted to post a few more videos this week because next week is Thanksgiving and I'll be doing that thing. So I'm typically kind of averaging 2 videos a week, and so decided maybe do 4 this week, and maybe do one Thanksgiving, the weekend after Thanksgiving. I don't know. All right, guys. So that's it. Hope you learned something. Ask me, hit me up if you have any questions about this stuff. Ask respectable questions, get respectable answers, and I'll see you in the implementation video. All right, y'all.